Problem 6. Matthew has a deck of 300 cards, numbered 1 to 300. He takes cards out of the deck one at a time and places the selected cards in a row, with each new card added at the right end of the row. Matthew must arrange that, at all times, the mean of the numbers on the cards in the row is an integer. If at some point there is no card remaining in the deck which allows Matthew to continue, then he stops. When Matthew has stopped, what is the smallest possible number of cards that he could have placed in the row? Give an example of such a row.
Right, so for the purposes of this exposition, my name is Matthew. Now we'll do some experiments at first just to get a feel for the problem. What Matthew has to do is to pick a sequence of cards on which are written numbers between 1 and 300, and at every stage the average of the numbers picked so far has to be an integer, a whole number. So let's do it. I think I'll pick 13. I picked 13. Let's see, the average of 13 is 13. So, all right so far. Now I've got to pick a second card, but this time it won't be so easy. I've got to arrange that the average of the sum will be an integer. So I'd better pick an odd number, so that two odds will add up to an even, so when I divide by 2, I'll get a whole number. Now, between 1 and 300, there are 150 odd numbers. So there are lots to choose from. I'll choose 13. No, I can't do that. I've already chosen 13. So I'll choose 7. Oh, very good. So now I'm supposed to put this on the right, and the average of these two numbers is 20 over 2. It's 10. It's an integer. That's fine. Right, now it's going to get slightly more tricky. I want to choose a card so that the average of these 3 numbers will be an integer. So the sum of the 3 numbers has to be a multiple of 3. So what really matters is remainders on division by 3, isn't it? Because these 2 numbers add up to 20, which is 2 more than a multiple of 3. I'll be okay provided I pick a number which is 1 more than a multiple of 3. Because if you add 2 more than a multiple of 3 to 1 more than a multiple of 3, you get a multiple of 3. Right, so I focus upon the numbers which are 1 more than a multiple of 3. How many of those are there in the range 1 up to 300? There are 100 of them, 300 over 3. I've used 2 of them already, but fortunately there are plenty left, 98 I think. So I'll choose one, a number 1 more than a multiple of 3. How about 100? Ah, there it is. Right, those 3 numbers add up to 120. Now I've got to put down a new card, and when I put down the new card, the sum of the 4 numbers has to be a multiple of 4, so that the average will be an integer. Now, these 3 numbers add up to 120, which is already a multiple of 4. If you like, it's a 4 times an integer plus 0. The remainder, when this is divided by 4, is 0. I need to add an extra number, which is also a multiple of 4. And there are lots to choose from, and I'm getting fed up with this lark. So there are, let's see, 300 over 4, which is 75 numbers, which are multiples of 4 in the range 1 up to 300. And I've used 1, so I pick one of the other ones. I think we've learnt enough from this game. So let's try to use our experience in how we pick these cards to write down some proper maths. Okay, so let's see when we can pick an nth card, where n is a number, we don't know what it is. So the idea is we've already picked n minus 1 cards, and at all stages so far the average has been an integer. I want to pick another card, so I have to be careful about remainders. So let's write this up. We have picked n minus 1 cards. The sum so far is, let's say, S for the sum. And I want to pick an nth card, so what matters is the remainder when S is divided by n. So we'll suppose that S is a multiple of n plus a remainder. We've seen something like this in one of the earlier questions. So here, Q and R are integers, and R is strictly less than n, and it's at least 0. Right. Now I want to pick an nth card so that I get a multiple of n. So it's important that I add to this sum a quantity which is n minus r more than a multiple of n, because when I do that, r plus n minus r will be n, and everything inside will be a multiple of n. Right, that's the plan. So let's look at the numbers which leave n minus r on division by n. So let's write out the small ones. Well, the smallest number I might pick is n minus r, and n minus r plus 1 times n would also do. That's n minus r plus a multiple of n. And then there's n minus r plus 2 times n. And let's keep going until we get up to, I don't know, n minus r plus n minus 1 times n. How many numbers have we got here? Well, it's the multipliers that give it to us. We've got 1 and 2. Back here there was really a 0 times n, and we go up to n minus 1 times n. So we're really counting the numbers from 0 up to n minus 1, and there are n of those. So here we have n numbers. And they're all n minus r plus a multiple of n. Now, if these numbers were all amongst the original 300 numbers on the cards, I can carry on, because I've used n minus 1 cards already. So the most of these numbers, some of them may have been discarded, but at most n minus 1 of these numbers has been discarded. And there are n of them, so there's one left. And so I can continue. Right, so the important thing is that all of these numbers should have been on the original cards. I don't know what r is. This is the largest number, and r is 0 or more. So this number here, it's at most n plus n minus 1 times n, and when you tidy that up, you get n squared. So provided n squared is less than or equal to 300, then I can put down my nth card. Well, the largest square, which is less than 300, or less than or equal to 300, is 289, which is 17 squared. Well, using this result from the beginning, I can put down a first card and a second card and a third card, and at every stage I'm trying to put down an nth card where n squared is less than 300. And everything's fine until I put down the 17th card. And when I've done that, this result runs out. And I no longer have a guarantee that I can put down an 18th card. I don't know if this is going to work, but maybe 17 is the answer. Maybe there is a sequence of 17 cards I can pick such that there is no 18th card I can put down. So let's go looking to see if we can find such a sequence of 17 cards. Right, so in our hunt for a sequence of 17 numbers which can't be extended, we can see from our earlier arguments that we need to use up all the numbers which with a particular remainder on division by 18. So let's just try and see if it works. So the smallest possible positive remainder on division by 18 is 1. So let's look at the numbers which are one more than a multiple of 18 that were on the cards. There's 1, 19, 37, and then lots more. And the largest one is 289, which we saw earlier because it was 17 squared. But it's also one more than a multiple of 18 because of that difference of two squares argument. 18 divides 17 squared minus 1, so 17 squared leaves remainder 1 on division by 18. That's just an aside. Right, so supposing we've written these numbers down. I don't know yet that there's a way of writing them down in a legal way, but let's worry about that later. Suppose there is a way of writing those down so that at every stage the average of the numbers written down so far is an integer. Okay? Now, what's the sum? Well, I don't want to add those up, but each of these numbers is one more than a multiple of 18, and there are 17 of them. So if I were to add these numbers up, their sum would be a multiple of 18 plus 17. So to continue, I would have to find a card with a number on it which was one more than a multiple of 18. But they've all been used. So I can't carry on. And I might be onto a winner. I might have found a sequence of length 17 which can't be extended. So provided we can find a way of putting down these 17 numbers so that at every stage the average of the numbers we've put down so far is an integer, then we've won. Now it turns out that doing the obvious thing actually works. If you put them down in increasing order, the average of the terms at every stage is a whole number. 1, the average of 1 is 1, the average of 1 and 19 is 10, the average of these three numbers is also an integer. You carry on. Right, that's true, and we've finished the question, but it's not very satisfactory. What are we really doing? Well, when you add up a few of these terms are lying in an arithmetic progression. That's to say you've got a first term, and then you keep on adding on 18 at every stage. And it's easy to understand the sum once you realize that you're adding up an arithmetic progression. This is how it goes. So the first term is A. The next term would be A plus the common difference. The next term would be A plus twice the common difference. And you carry on, and the teeth number would be A plus t minus 1 times the common difference. Now, there's a formula for the sum of an arithmetic progression, but I don't expect you to remember it. I'm sure it's in a formula book somewhere. So I want to work out the sum, but not in a way that's very stressful. So let's let the sum be, I don't know, capital S. Right, so capital S is the sum of all these numbers. So the trick, you've probably seen this before, is to add this up twice. So I'll work out not the sum itself, but twice the sum. And the way I work it out is this. I go, this is added to the last term. So I get 2a plus t minus 1d. And then the second term I will add to the term which is the penultimate term. And the sum of those two terms is, well, what's happened? This one's gone up by d, that one's gone down by d. It's the same. And then I add the third term to the antepenultimate term and carry on. At every stage, the sum of the pair of terms that I'm picking is this. And there are t of these. So I've got a valid equation. Now, what I'm interested in is the average value of the terms in the sequence. So I know how to add them up. What I need to do is to divide by 2. And what I also need to do is to divide by t, the number of terms in the sequence. So the average value is going to be s over t. And that's going to be 2a plus t minus 1d all over 2. Right. It's still a bit algebraic, but think about what this is. We've seen this before. This, after all, is the average of the first and the last terms. If I added that to that, I would get this numerator. So park the algebra. Think about what's going on here. The average of a t-term arithmetic progression is just the average of its first and last terms. Now, when we're adding up our terms of this arithmetic progression, doesn't matter how many you take, the average of an initial fragment of this arithmetic progression will be the average of the first term and the last term, whatever it is. That is, it's the average of two odd numbers. And two odd numbers add up to an even number, so the average is an integer. So it works. If you wanted, you needn't put these numbers down in that order. The argument shows that you could put them down in the reverse order, and at every stage, the average of the numbers put down so far would be an integer. And actually, there are lots of other sequences of length 17 which all have the property that they can't be extended to a sequence of length 18. And it might be a worthwhile investigation if you try to find some.